Okay, so this is my first attempt at ensemble docking. So this is a bacterial RNA polymerase, and it is it's essential for the survival of various bacteria, tuberculosis in particular. So it's an anti-tuberculosis target. So I tried to follow the same recipe that Romy did. You know, I ran molecular dynamics simulations on this, which was no small feat. It's a really big system. There was around 600,000 atoms when it was fully solvated. Took a lot of computer time. I clustered it, so I generated like 20 clusters, docked into the centroids using Glide, and I docked the zinc lead-like library, if you're familiar with that. It's basically, it applies some filtering rules, some of which Vicky talked about in the last lecture, to reduce the size of the zinc down to something more tractable. Anyways, huge effort. I was really invested with it, and it took 8 or 9 months. And we did the experimental testing. I had these collaborators at Rutgers. They were field leaders with bacterial RNA polymerase. It was just a golden project, and it didn't work out at all. Like I got no actives, none. Now some of this could have been come down to the compound library that I used. I could have made a mistake somewhere. That's perfectly reasonable. Anyhow, the upshot of this was I did all this effort, and I didn't get any good results. Okay, so naturally I asked the question, well, why didn't I get any good results? Then I started thinking about, well, the success of a virtual screen depends on which conformations that you're docking into. So if you have a large collection of conformational states and you have to pick out a subset of those, which do you pick and why? And so that's kind of the question that motivated this talk, and that I'll provide one answer to over the next several slides. Okay, so we need some metric to evaluate how we're doing as computational chemists in terms of our virtual screens. So virtual screening, kind of in its essence, is it's a binary classification problem, right? We're sorting apples from oranges, right? We're sorting actives from inactives, right? One from the other, binary classification. So let me walk you through this figure. So say you have 1 million compounds, and you dock all 1 million compounds, and you generate 1 million scores. Now you have a list of 1 million scores, and you make a histogram of all those scores. Well, that histogram would look like this curve here, for example, in black, right? But this curve in black, because those 1 million compounds are composed of actives and inactives, can be kind of decomposed into two underlying curves. The blue curve on the left and the green curve on the right. So schematically, what we're doing during virtual screening is we're saying, well, let's set a score threshold, and all the compounds that have a score lower than that threshold, a higher predicted binding activity, will assay. So all of the compounds that are under the blue curve, or the fraction that's under the here, are going to be your actives. These are your true positives. So these are the things you predicted to be active that are actually active. And your false positive fraction is everything to the left of your score threshold under the inactive curve. They're inactive, but because they're to the left of the score threshold, we're saying they're active, but they're not. So these are the false positives. So by sliding the score threshold from negative infinity to positive infinity, and integrating the area under the probability distribution functions, we can get these curves that represent our true positive fraction and our false positive fraction. If we plot the true positive fraction against the false positive fraction, we get something called a ROC curve, or receiver operating characteristic curve. Okay, so this thing has utility for evaluating virtual screening performance in two ways. One is globally, the other is when you're considering early enrichment. So the global performance metric is the area under the curve, right? when the area under the curve is equal to the probability that your model will rank an active ahead of an inactive. The higher the probability, the more utility your classifier has. But as computational chemists carrying out a virtual screen, we're not necessarily interested in global behavior, right? Because really what we're doing is we're ranking a whole list of compounds. We don't care how the actives and inactives are ranked globally in the whole list. We want to look at the top fraction. And so if we focus in on the early part of the curve, we can calculate something called an enrichment factor, which is just the ratio of the true positive fraction at some arbitrarily defined false positive fraction. So typically, well, going forward, I'll describe the enrichment factor at a false positive fraction of 0.001% or 1/1000th, which, for the sizes of the database that I'm talking about, usually means 6 to 8 inactive compounds. Right? So in other words, you'd go down the rank list, you'd count up 6 or 8 compounds, 6 or 8 inactive compounds in your rank list, and then set your score threshold and then count up how many actives you have in that list. And kind of, the ratio of the true positive fraction and the false positive fraction gives you this idea of early enrichment. Okay. More on rock curves. I guess this is kind of unnecessary, but I'll just, walk you through it. So the same thing, you dock 1 million compounds, you generate a distribution of docking scores. That black distribution is composed of a distribution of actives shown in blue and a distribution of inactives shown in green. You can see here that the distributions of actives and inactives are identical. In other words, your virtual screen has zero ability to separate actives from inactives. Your true and false positive fraction curves are going to overlap. And when you plot one against the other, you'll get a diagonal line that bisects the unit square. If you take the area under that diagonal line, it's just 1/2 of 1, which is 1/2. So the AUC for a virtual screening metric that performs randomly is 1/2. So 1/2 is bad, right? If we get 1/2, your method is not doing as well as you would like it to do, and you should go back and think about it more. When your methods start pushing the active curves from in the inactive curves apart, your AUC tends towards 1, and your enrichment factors also are driven up. So when you separate your actives from your inactives better, your AUC tends towards 1, and your enrichment factor goes up. Okay. So yes. ROC stands for Receiver Operating Characteristic Curve. And I don't know why they call it that. This was generated back in the 1950s by some really smart scientists that were looking at radar signals or sonar signals, and they wanted to, kind of say, well, is this a whale or is this a submarine? And they used this idea of receiver operating characteristic curves to train their threshold for their sonar signals. So I don't know, it's a military thing. Okay, so we can evaluate the performance of our method using these ROC curves. Now a word on how we train and test models. So generally what we'll do is we'll take some full set of compounds shown here in green. Now these are compounds that are composed of known actives and known decoys, right? So this is a caveat when you're training a model. You have to have information to train a model. If you don't, if you're working with some neglected tropical disease target, for example, then you can't train a model, you can't validate it, so you can't be sure how it's going to perform. But if you're working on a well-vetted target and you have active and inactive information, then you can go through this process. You take your actives and your inactives, you randomly split them apart into training sets, shown in blue, and test sets shown in red. You take your training set and you use it to make a computational model. Then, with your model, you ask, well, how does it do on an independent set, right? So when you generate your model, really what you're trying to do is most optimally separate the actives and the inactives in the training set. So you're using the information contained in the training set to generate your computational model, but you want to make sure your computational model performs robustly, right? And to determine whether or not it performs robustly, you want to assay it or interrogate it against an independent set whose information doesn't overlap with the training set. And that's this idea of interrogating it against the test set. Once you're sure your model is robust, then you're basically at the finish line here, and you apply it prospectively. Now you go out and you take your e-molecule set and you screen it, and then you recommend those results to your experimental colleagues, and you get back numbers. And maybe you sucked, and maybe you did great, and hopefully you did great, because it sucks sucking. All right. One more note, statistics. Typically, when we're doing a virtual screen, we have one or more computational models that we're comparing, right? I'm a computationalist, and I can, there's virtual screening. I have docking methods at hand. I could use a pharmacophore model. I could do fingerprint methods. I could do ensembles of fingerprints or ensembles of structures. The point is that there's a lot of different models that I could apply to carry out a virtual screen. And so usually what I'm doing is I'm comparing one model to another. And I want to know if model B does better than model A, what are the chances that model B did better than model A, just due to random chance, right? Because the performance of model B depends on the composition of compounds in the set, right? So the composition of compounds might have been randomly chosen such that model B actually did better than model A, but if you look at the performance of model B against model A, on average across a lot of independent sets, well, model A will actually do better than model B. And that's where statistics comes into play, and specifically this p-value. The definition of a p-value is here, but basically when you see a small p-value, think that the method that's doing better is doing better in a statistically robust way. So smaller p-values are better. It's statistical significance is usually something that's used here, and usually you say a result is statistically significant if the p-value is less than 0.05, right? But you could set the p-value to anything you want. And then confidence intervals, they basically tell you the variability that you might expect from your results. So for example, 95% confidence interval is something you'll hear often. What that means is that if you carry out 100 virtual screens and in each virtual screen you set your confidence interval identically, in 95 out of 100 of those virtual screens, the true population average performance of your model will be within the 95% confidence interval. Wider means more variability. Narrower means less variability. This is basic statistics. Okay, so we talked about how we're evaluating our virtual screening method. I introduced these things called ROC curves. I said statistics are important, so we're going to be looking at that. And I asked the question, I was like, well, how do you know which conformations are going to form the highest performing virtual ensemble? Highest performing ensemble. So now let me describe how I answered that question, or how I attempted to answer the question. One is with this exhaustive method, exhaustive training. So we take our compound set, we split it in half. Now we have a training set. And let's say that we have 3 conformational states, right, represented by the red, the blue, and the green structures. So we'll dock into each of these conformational states. Again, they could be crystal structures, they could be cluster centroids from an MD simulation, they could be NMR structures, whatever you want. We dock into these things, and we get AUC values, right, and we get enrichment factor values independently for each set, each of these things. And now what we want to do is form ensembles of them, right? So for a one-membered ensemble, it's a small ensemble. It's not really an ensemble. It's just a one-membered. For a one-membered ensemble, you can have there's 3 different one-membered ensembles. There's a red one, a blue one, and a green one, right? So you can rank the performance of the one-membered ensemble either by the AUC or by the enrichment factor, and you just retain the best performing one-membered ensemble. Right? So maybe it's the red one, for example. Now, if you want 2-membered ensembles, you have to make all pairs. So you have red and blue red and green, and then blue and green. So that's all possible two-membered ensembles when you're choosing a set of 2 from 3. And again, you can just take the highest performing member. Three-membered ensembles, there's only one way to make a three-membered ensemble from a set of 3 conformations. It's just all 3. Now you have, you've got 3, and 3 is 6, and 1 is 7. Now you have 7 different conformations, 7 different ensembles that you've constructed from a set of 3 different conformational states. You know how each of them perform on your training set, so just pick the best one, and then ask how it does on the independent test set. And if it's robust, go ahead and use that for a virtual screen. Okay, so scaling. This, if you kind of go, oh yeah, I remember this from algebra. I really liked algebra. Yeah, who likes algebra? Okay, nobody. Good. Sasha, thank you for the charity laugh. Okay, so this is the, if you can't count on your lab mates for charity laughs, who can you count on really? So the total number of evaluations, right? So the total number of AUC values or enrichment factor values that you have to carry out is the sum over n choose k, right? So when we have 3 members, 3 conformational states that we're choosing from, n is 3, and we're selecting 1, n choose k is 1. 2 choose 3 is 3. 3 choose 3 is 1. We're summing up all of those, and that should give us 7. When n gets big, the scaling, and here's a little derivation, the scaling goes as 2 to the n. Okay, so you can actually see the scale here. This is 12 times 10 to the 11th for, docking into 40 different conformational states. So you'd have to carry out on, what a billion is 10 to the 9th. So, 1,200 billion independent evaluations. So that gets to be, computationally intractable unless you want to split the problem on a supercomputer. But it's a lot of effort. So the scaling for this is, not super duper. Nevertheless, how does it do? So to evaluate how it does, let's look at a test system here. This is the androgen receptor. Androgen receptors are nuclear hormone receptors, so they bind to greasy molecules, typically steroids. They have like a cholesterol-like backbone. They bind to these things, and then upon binding, they enter the nucleus and initiate transcription. Okay, so the upshot of this whole slide is that I ran some molecular dynamics to generate 100 nanoseconds of trajectory. I clustered it using POVME that you played with yesterday, and I generated 10 clusters. Then I used Glide SP from Schrodinger to dock into each cluster centroid. And when I was doing the docking, I used something called the DUD-E, which is the Directory of Useful Decoys extended, affectionately called the DUDE. So I docked I generated my training and test sets using the DUDE, and then I trained to maximize the AUC and the enrichment factor using the exhaustive method.
What's the difference between this extended DUD set?
The extended DUD set and the DUD set is, so the original DUD has 38 targets, and the extended DUD has 102 targets. So, it's just bigger. Okay, so here's a slide. Here's a results slide. So on the left is where I was training to maximize the AUC value. This histogram is a distribution of, okay, so I docked into 10 different centroids, and I made ensembles of size 1 to 10. And so that ends up being around just over 1,000 different ensembles that I could construct. Each one of those ensembles has an AUC value, and if I bin the AUC values, I get this histogram distribution. And the nature of the method is that it guarantees that you're going to pull out the ensemble that performs very best overall on the training set according to the classification metric that you're interested in, which in this case is the AUC, and in this case is the enrichment factor at a false positive fraction of 0.001. The crystal structure AUC is 0.75. For the training, it's 0.89, so we get a performance boost there. 232 versus 214. So on the training set, when you train it, it seems to do better than crystal structure, which is good. The optimally performing ensembles are shown here in green. There's of size 6 for maximizing the AUC and of size 4 for maximizing the enrichment factor. And the confidence intervals are shown by vertical black bars. Okay, so on the test set, and this is really how the methods do. There is information in the training set that we use to train the model. The test set, we don't know anything about it, so we're asking how the classifier classifies something it doesn't know anything about. The black line here is the training set AUC values. The red line is the test set AUC values. In green are the best performing ensembles on the training set. So really what we're doing is we're pulling out the ensemble of size circumscribed by the green box. And you can see that there is a performance dip. It's just inside of or just outside of the 95% confidence interval. It's relatively robust, so it seems to be fairly decent. The AUC on the training set is 0.85, and the AUC of the crystal structure on the AUC on the test set is 0.85. The AUC of the crystal structure is 0.71 on the test set. So we're outperforming the crystal structure on the test set when we look at AUC values. Not so for the enrichment factor. 151 for the train method on the test set versus 178 for the crystal structure on the test set. Okay, so if you're just basing it on this, probably pick the crystal structure because it's less work. Nevertheless, here's a training method. Okay, so the exhaustive method scales as 2 to the n, right? So the scaling's bad. So here's a faster heuristic. Same sort of deal. We were docking into 3 conformational states. The first method is the same. We rank the conformers by the AUC value or the enrichment factor value. And we retain the best performer. Say it's red. So now the red member is our optimally performing ensemble of size 1. All right. So that forms the seed for our second ensemble member. Now we'll take the red guy and we'll pair it with each of the remaining structures that haven't been grouped into ensembles. So we'll pair the red with the blue, we'll pair the red with the green, and we only have to evaluate 2 different ensembles. With the exhaustive method, we had to evaluate 3. In the third member, we just, we pull everything together and we evaluate it. So if you're looking at how this thing scales, the first time out of the box, you have to do n evaluations, right? 1, 2, 3 here. And for the second evaluation, you have to do n minus 1, so, 2. For the third evaluation, n minus 2, right? And you can go on down to just 1. If you rewrite the sum and you get this expression here on the right, if you take the limit of this as n approaches infinity, you see that the method scales as n squared, which is much faster scaling than the exhaustive method, demonstrated by the curves here. Here's the exhaustive method in black. Here's the faster heuristic in blue. So scaling's better. So how does it do? Here's the training set again. Here's the same histogram that I showed you last time. The value from the exhaustive method is shown in black. The value from the faster heuristic is shown as a dotted or a dashed red line. And you can see that they virtually overlap. So they're nearly identical. Same thing with when you're training to maximize the enrichment factor. The ensemble, the performance metrics of the ensembles identified by both training methods have identical performance on the training set. What else can I show you? I think most of this other detail I'm going to skip over. So how does it do on the test set? So in black, we have the AUC values plotted as a function of size for the exhaustive method. and the dashed red are the AUC values plotted as a function of ensemble size for the faster heuristic method. The curves are identical because they identify identically performing ensembles, but at a much faster speed. The enrichment factor values, you can see slight differences in the shape of the curves. So there are differences in the ensembles identified by the two methods when you're training to optimize the enrichment factor value. And again, we see that looking at early enrichment, the crystal structure seems to outperform the best ensemble, which is a shame. And again, if I were doing this and applying it prospectively based on these results, I would take the crystal structure method. But what this also illustrates is that the faster heuristic performs comparably to the exhaustive method. So in this case, unfortunately, ensemble docking is maybe not the way to go if you're interested in the enrichment factor, but the methods seem to be robust. Okay, so the faster heuristic method scaled is n squared compared to scaling 2 to the n for the exhaustive method. So a much faster heuristic is this one. This one is going to scale as O to the n, and it works as follows. So you dock into your 3 conformational states, and the way you generate ensembles is just by ranking your conformational states by their performance, and then just kind of, your 1-membered ensemble would be your best performer, your 2-membered ensemble would be the 2 best performers, and your 3-membered ensemble would be the 3 best performers. So you only have to do n evaluations, and that, of course, is O to the n scaling, or linear scaling, which is about as fast as I can go. Here you can see the differences in the scaling. The black curve is the exhaustive, the blue curve is the faster heuristic, and the green curve is this much faster heuristic. It's kind of okay. So how to do? Here's the same curve, same deal as the last few slides. The black is the exhaustive method. The dashed red is the faster heuristic, and the dotted dashed blue is the much faster heuristic. And if you look at the vertical lines there, you can see that they're nearly overlapping. If you can consider the statistical significances of the differences, there is a statistical significantly different. The difference between the exhaustive and the much faster heuristic is statistically significant at the 5% level. This shown in green here is the method identified by the faster heuristic, and it is significantly different according to statistics than the exhaustive training method. And if I train to maximize the enrichment factor, I get identical solutions across all 3 methods. Okay, so on the test set, again, the black shows the performance of the exhaustive training method. The blue shows the performance of the much faster heuristic. You can see that they're more or less overlapping for the AUC and somewhat not really overlapping for the enrichment factor values. Again, we're outperforming the crystal structure in terms of AUC value, not so for enrichment factor. And the much faster heuristic doesn't perform as robustly as the 2, but it's faster. Okay, so show of hands, who's going to sleep? Okay. So timings, this is a shameless plug for Max. I can see that some of you have not yet converted to Max. There's a Dell there. That's a shame. Hewlett Packard, it's okay. So I would really strongly encourage you all to go purchase MacBooks. They're aesthetically very pleasing, and the operating system is it's just fantastic. I have a Mac myself. Okay, so the timings were run on my MacBook. This was for optimizing ensembles when you're taking a set of 10, you're starting with a set of 10 conformational states, and you're determining the subset of that 10 that performed optimally given your classification metric of interest, be it the AUC or the enrichment factor. So for the exhaustive method, maximizing the AUC value, it took 260 seconds, so that's like 5 minutes. And this is on one core. It doesn't really take that long. Docking is the bottleneck, but if you're docking into, or if you're making ensembles of, ligands, if you have, your number of ligands for a typical target that's been well prosecuted, like a kinase, might be on the order of hundreds. So if you're pulling a subset of 100 different ligands to form an optimal ensemble, this 260 seconds is going to blow up very rapidly, and the exhaustive method is going to become intractable. The faster heuristic takes 7.8 seconds, and the much faster heuristic took 1.5 seconds. So the much faster heuristic doesn't perform quite as robustly as the exhaustive method, but it's a lot faster. And you see a similar timing trend for when you're maximizing the enrichment factor. All of this has been built into a Python application called Ensemble Builder. Basically, now it's command line driven. This is what the command line looks like. There's currently 5 different modes. The exhaustive method, the slow heuristic, which confusingly is the faster heuristic method that I described in the slides, and then the fast heuristic, which is the much faster heuristic that I described in the slides. The scaling is given over here on the right, so you know what you're dealing with. There's a splitter function that will randomly generate training and test sets from your input set. There is a limitation on the input. You do need to provide a CSV file. I go into gory detail about the exact formatting for the input in the hands-on session. And then finally, there's this post-analysis function that allows you to generate tables that look like this. So for example, you can determine the performance of different ensembles by their AUC value, get some statistical information, their enrichment, and again, the confidence intervals. You can also compare different methods, getting p-values for the differences and p-values for the differences and 95% confidence intervals. And you can output things like ROC curves. And so collectively, this set of information should help you make an intelligent decision about what method to use or not to use, as the case may or may not be. Conclusions and caveats, right? So the exhaustive method is robust. It scales poorly. The fast heuristic does just as well as the exhaustive method on the test set that I looked at, but the scaling is much better. The ON scaling method does reasonably well, although not quite as well as the exhaustive method. And all of these, or the faster methods should allow you to do neat things like make ensembles of not only receptor conformations, but also receptor conformations and two-dimensional ligand fingerprints and three-dimensional pharmacophores. And so all of that stuff is kind of in the works. But now that we have methods that scale reasonably well for larger number of input states, we're in good shape to make progress in that area. The caveats, as I said before, if you're interested in neglected tropical diseases where your target has no known actives and decoys, you're kind of up the creek without a paddle. You can't train methods. It's just, that's just the nature of model training in general. If you don't have any experimental information that you're trying to reproduce, you cannot train a computational model. It's true even for Newton's laws, which are nominally physics-based, right? Okay, so training with known actives may bias the search towards similar compounds. So if you're looking for novelty or diversity, this might not do it for you because you're using information and you might get that similar information back with a trained model. Performance variability, it depends on targets. So, once you train a method, it might not be as robust on one target as another target, and so you have to be cognizant of that. And finally, there's perhaps more appropriate virtual screening methods in Ensemble docking. If you listen carefully to Vicky's talk, she gave you a lot of very simple filters that you can use to throw out the crap, throw out the swill, the Rios methods. That's a really quick way to just cut your library size in half, which can prevent the old pipetting monkey at the beginning of the talk from developing carpal tunnel syndrome. And we all love pipetting monkeys, so let's be aware of that. So thank you for listening. Thank you to Romy, to CD, who is no longer in the back, to Tavina, who's not here. These are all my group members. I'd like to especially say thank you to Sasha for laughing at my stupid jokes. She's also an Amaro group member. And this is my newborn son here, who's now 6-month-old. And he wants to just say he appreciates you tolerating his ill sense of humored father as he's been spouting on up here and saying silly things. And thanks you all for for listening.